So we are looking at the parabola f of x equals negative x squared minus 2x plus 3, and its derivative function f prime of x equals negative 2x minus 2. Now, one of the most important things to note here is that I designed these two graphs so that their x-axes would line up. That is to say, x equals negative 1 lines up exactly with x equals negative 1. X equals positive 3 lines up with exactly with x equals positive 3, and so forth. The reason for this is that the output value of the original function is a y coordinate, a y value. The output value of the derivative function is actually an instantaneous rate of change. But the x values are the same. So for example, if I wanted to know the derivative at the point 1 comma 0, I can evaluate the derivative function at x equals 1. Same x value. So the graphs are drawn so that the x values line up between the two of them. Now, the idea here of the graphical comparison is to see how they relate and to understand the relationship between them, to see that there are certain characteristics of the function itself that the derivative function is also displaying, albeit in a slightly different way. One of those things, well, two of those we've actually already found, that at certain points, the value of the derivative function corresponds to the slope of the tangent line at that point. We have already done that for a few points. For example, we did not do that one. We did this one. Negative 2 comma 2, a point on the graph of the derivative function. That is to say, when the x value is negative 2, the instantaneous rate of change of the original function is 2. If we come up to this point on the original function, and we draw a line with a slope of 2 through that point. Now be careful of the scale here. Note that on the y-axis, the scale is going every 3 blocks is a whole number. So a slope of 2 means that it needs to go up 2 whole numbers and to the right 1 whole number. So if I connect those 2 points, and I draw a line with a slope of 2 through that point, sure enough, that line is tangent to the parabola. We saw another such point. One comma negative 4. Meaning that at the point on the original function, whose x value is 1, the tangent line should have a slope of negative 4. So, since we don't go too far downward on the scale, we can reverse that and, of course, go left 1 and up 4. So if I connect this point where it's tangent to the graph to this point up here to draw the tangent line, if you'll excuse the fact that my graph is not entirely accurate and using a sketch pad here, we get a line that is, sure enough, tangent to the graph of the parabola. Now, a few things I do want to point out. If we were to draw a tangent line to this parabola, anywhere at any x value up to the vertex at -1, at any x value up to -1, the tangent line would have a positive slope, as evidenced here, or even a little bit closer in. Not only would they all have positive slopes, we could see a trend. The tangent line is steepest as we are far to the left. Still steep, but not as steep. And considerably less steep as we go inward towards x equals 1, or x equals -1. If we look at the graph of the derivative function, we see a similar trend, not in tangent lines, but in the output values of the derivative function. We get the largest positive values far to the left of -1. Still positive, but not as steep, not as large. Still positive, but not as large. And the closer we get to x equals -1, the closer the values of the derivative get to 0, which would be a perfectly flat horizontal line. And sure enough, if we actually go up here at x equals -1, a tangent line at x equals -1 would actually be a horizontal line, so that the parabola comes up, just touches the horizontal line before traveling away again. From there, we start out with negative slopes. Small at first, not very steep, and then steeper, and then, as we get further down, even steeper. And of course, what we see on the derivative function is that once we pass x equals -1, we have negative, of course, but small in magnitude. Over here, a much steeper tangent line and a much larger in magnitude negative value for the slope. This kind of comparison of the graph of the original function and the derivative function will allow us to verify that our answer even makes sense. Now, like with other graphical limits, the exact values are not always readily attainable, and not always easy to demonstrate. Certainly, as we look at some of these, we can see the differences in steepness, but it's hard to measure the actual slope of that line without extending it all the way. And even then, we'd have to have it drawn exactly accurate to get the exact value of the slope. So, as before, the graphical approach is not about get the exact values, but it is about understanding the general trend of what we're looking at. The fact that when we have the largest positive values of the derivative is when we have the largest positive sloped tangent line, the steepest positively sloped tangent line. When we have smaller positive output values of the derivative, we have smaller or flatter sloped positive, but still positively sloped tangent lines. At the place where the derivative is 0, we have a completely flat, a completely horizontal tangent line. And then the same with the negatives. When we have small negative values of the derivative, we have relatively flat, negatively sloped tangent lines. And as we get to larger negative values of the derivative, we have more steeply, negatively sloped tangent lines. This kind of comparison is useful and should be done, I think for now, for every function that you do. It doesn't take long to sketch the graphs, and they don't have to be perfect. This being a demonstration, I used graph paper and drew them as accurately as I possibly could because I wanted everything to line up as perfectly as possible. But the idea is to get just a general gist of whether your derivative function is actually correct. So I highly recommend that for now, for any function that you find the derivative, sketch the original function, and then beneath it, sketch the derivative function in such a way that the x values all line up. Note that the scale on the y-axis is different between the two. That is okay because the output values of the original function and the output values of the derivative function are completely different things. They have completely different meaning. If this was, say, a position function, and its derivative would therefore be velocity, the output of a position function would tell you the location of an item. The output of the derivative would tell you its velocity. So again, they do not need to be the same. They could be completely different from each other, and that is okay. But the x values must be consistent. That's why we don't draw them side to side. We draw them up and down to keep the x values aligned between them. So again, I highly recommend this kind of graphical analysis. Even if you don't do it for every problem, do it certainly for some of them for now, to get that feel for whether the derivative function you found is even valid, because let's face it, at this point in time, the derivative is a new concept. It requires a little bit of complicated algebra. And at the end of it, what did we even find? This will help you to understand what it is you even found. So I highly recommend that you do this. We will actually use this technique in a later lesson to help find the derivative of, say, the sine function, which algebraically is going to be a little tricky. Graphically, though, we can easily compare our result from the algebra and make sure that it actually is valid. So we'll see this kind of comparison again in class, but it's certainly a good idea for you to do now so that you understand what it is you're actually finding.